will stick farther. This is an interesting problem because we don't have all the information pretty much. I mean, it definitely is possible in some of these locations here to just be like, hey, don't make a slope where this happens. Because we can definitely do that. You know, like, well, just make sure that, you know, go through your geometry of your level and make sure that this absolutely never happens. And that's not a big issue, actually, for some of this. .517 is all screwed up. Extra stick was 0.000031. Why is that? So I guess our movement direction vector z was like super small or something? Well, let's find out. Movement direction vector was 1, -1? What the fuck? That's XYZ. The movement direction vector was literally straight up. So that means we actually ran into the corner of this object when we moved. That cannot possibly be correct. So it's like we're getting the wrong normals for our movement. And this is why things are never as simple as blah. It's because the information we're getting is not correct. Alright, so the movement distance was 93. The impact normal was, the movement direction vector was great in the y and small in the z. So the impact normal was 1 in the y? The impact normal was 1 in the z. So we're moving directly to the right. So it looks like we're taking the slope that is the least. We're taking the slope that is the most vertical. And that's going to be our slide normal. Looks like we're not actually changing the collision. So what is actually going on here? That we're getting the flat surface for the collision and we're not. Well, this is just. So when we are actually directly on top of this thing, the normal to the collision, even though we're on a point here, the normal to the collision is going to be the inverse of our box. So we're actually our normal to our collision. We are standing on flat ground according to the physics system right now. So it's that we are moving so quickly to the right that we actually are able to do something. That means that the base floor stick distance probably the base floor stick distance is not enough. It also means that we'll have issues with our movement. Yeah. So this is definitely calling into question the moment that we leave the ground. We need to resettle our object. So the solution definitely here is going to be seeing where we're actually moving. So it was like a 20 move. But what should have happened is basically we're on flat ground here, and then we're not on flat ground. So how are we calculating this calc stick? It's floor stick distance base plus dt times floor stick distance dt. So let's see, it's a movement data structures. So it's definitely not far enough. 20 is just too small for the stick distance. We could do a binary search for where we're sticking, where we leave. So that fixes pretty much our issues for all along here, but it's when we're going down these slopes. We can run into those problems. So the problem is on these slopes. Now flying when on ground. So it's 633 that's kicking us off. So let's see what's at 633. 633 is we're traversing a seam. So it was 633 again. Now flying when was on ground. The stick distance was 101. The movement direction vector was -1 in the z, so it was straight down was our movement direction vector. Yeah, again, -1 was our movement direction. So for that to be true, that meant that our collision had to be like basically vertical. Am I stuck right here? How in the hell did I get stuck in this object? Nah, that's not very good right there. Yeah, and we've got even... Yeah. It's another one of these issues here where we're getting stuck in an object. Now, did I have all these things here? Because maybe I... Yeah, that velocity is just wrong there. Like, we run off the edge super fast. Well, it's not wrong right now. It is wrong there. The movement direction vector is -1, which meant we were moving straight down? That can't... No, that's the Y. We're moving straight to the left. So what happened was we were attempting to traverse a seam. So what exactly is this doing? We've got the movement, sweep, collision, normal. So we were moving along our object and we ran into something. So what's happening is we're going along and we have an object that has a seam in it right here. This is two squares, and when we're running along, we're actually going to impact with something. But we're impacting with it with the bottom of our object. And because we're on the top of this object, the normal to the collision is 1, so we're flying off at this angle because we actually landed on it. And when you've got an object like this and you're colliding with it by sweeping downwards, if your object is like this at all, then the normal is actually going to be straight up. So what we need to do is move our object to the right by the width of the object and then cast it down to get the movement normal, therefore guaranteeing that this moves over properly. I mean, of course, that has possibilities for error, So what we need to do is actually get like the collision point and take our y. So you need to take like half our width, add our collision point y minus our y, and then add a very small number to that. And that should be to the left or right, I guess. So that should be the sine of the move y. So this is something that we should do if the movement is movement sweep collision normal dot y. We're going to need our test position. So it's going to equal our start position So it's going to be, do we have our extents inside of any of our stuff? It's like, yeah, we've got our F box. So we've got our mcache bounds.y. So we have the movement direction impact point dot y minus our start position dot y. So it's going to be sine multiplied by the width plus a tiny float. Let's actually crack open the global utils and see what that tiny float value is. Yeah, it's a small float, but it's not too big. So it's going to be the sine times the width, and then we're going to add in this y diff. So the test start is going to be the start position plus the start offset. And we're going to want to get our normal based off of this. So we're going to do a sweep downwards. So what we're going to want to do is the normal is actually going to be normal to the collision is going to be collision dot impact normal. Are we doing anything with this movement direction impact point? Well, I don't think we have to do anything with that. Alright, so let's get the current position. Let's get the offset. CD test start. Let's get the initial normal. Let's get the y current velocity. Alright, and the new normal is going to be there. Alright, so basically hopefully what's happening is when we're like halfway down this object, we get snagged inside of it, and what we're going to do is move in the direction of our motion by a small amount, which should make it so when we collide, we're going to collide with one of the corners of our object on the actual surface that we would be landing on. Impact normal collision dot. Is collision dot hit dot impact normal? So we moved our object over, so we'll clear our block, and it'll actually impact, instead of on the top of this thing, which is giving us the wrong normal, it's going to be over to the right, so it will actually hit the surface, as opposed to kind of the tip of the object. And we're going to do that when our movement sweep collision test is almost flat. So we should only be hitting this case when we're impacting the corner of the object, which is our flat object. And we had like the whole slide normal stuff coming in here, which was kind of what we were doing before. Collision stuff's just a bunch of edge cases. And now we're not even hitting this edge case. There it goes. Now flying when was on ground. That was 663. So it was this one. And we didn't actually do our... This should be our collision normal Z. It's a very small window there for us to get screwed up, but it's there obviously, so we're going to try to get it. And this is definitely not the super interesting sort of coding stream. Alright, so the current position was such, the current offset is -11, so we are going to the left, so we'd expect -11. The test start is... looks like to the left, so that's fine. The initial normal was that current velocity is this. The new normal is Z of 1. So the new normal was not there, so perhaps the offset was not big enough? Because the new normal, again, was 1. Hello, Nils Noah. How are you today? Let's see. We're going to go up here. Very good. We're just getting some edge cases of when we're running down these slopes sorted out. Whoops. Because we're running down these slopes, we're running into something wrong, and it's causing us to fly off like that. So let's see. You just made something super cool? Well, I don't know what you're talking about. What sort of thing did you make? Let's see. Our new normal is negative. So the new normal is negative and positive. So it's like this, which is correct. And then we were actually flying, so the direction vector, the movement direction vector was 1. So we're going straight up. So the new normal didn't actually work? We obviously need to print out the frame number on this thing.